There is a particular kind of cruelty in being destroyed not by the rival you feared, but by the one whose name you never bothered to learn. For years, Boeing's Starliner was supposed to be the safe bet. It was the cornerstone of NASA's commercial crew ambitions, propped up by billions in government money, the weight of aerospace legacy, and the quiet confidence of an institution that had been building rockets since before most of its competitors even existed. And then a small company out of Colorado showed up with a winged spaceplane called Dream Chaser. No louder engine, no bigger budget. Just a better heat shield, and with it, a way to win on every battlefield that actually mattered: public trust, technical reliability, the shape of the commercial future. So how does a giant fall, not to a rival it respected but to an afterthought? To understand why Dream Chaser's rise feels so seismic, you first have to understand how completely Boeing had already collapsed. Not in one catastrophic moment, but slowly, like a building rotting from the inside while the facade still looks intact. When NASA handed out its commercial crew contracts in 2014, the logic seemed obvious. SpaceX was the gamble, Boeing was the institution. SpaceX received $2.6 billion, Boeing received $4.2 billion. That gap told you everything about who NASA trusted. Boeing was meant to be the bedrock. Instead, it became the cautionary tale. The first uncrewed test in 2019 nearly ended in disaster. The second in 2022 clawed its way through helium leaks and valve failures. By June 2024, optimism had hardened into something closer to grim patience, and then it got worse than almost anyone had been willing to say out loud. Thrusters failed, helium leaks multiplied. What was supposed to be an 8-day mission for astronauts Butch Wilmore and Suni Williams turned into 9 months stranded aboard the International Space Station. When they finally came home, they came home on a SpaceX Crew Dragon. Starliner flew back empty. The investigation classified the mission in NASA's most severe failure category. The 6-mission contract was cut to 4. Starliner 1 was stripped of its crew and demoted to a cargo run, and even that has since dissolved. As of May 2026, launch opportunities remain under review with no date on the calendar. One of the most informed observers in the field summed it up bluntly: a slip into 2027 looks more likely than not. And when the people who know the most respond to yet another delay with a shrug, that tells you something has quietly passed the point of rescue. In commercial spaceflight, confidence is currency, and Boeing's account is nearly empty. Here is the part that stings most. While Boeing was losing astronauts in orbit and defending its failures in front of congressional committees, something extraordinary was happening in a quiet hangar in Ohio. A space plane roughly the size of a large SUV, sleek, winged, covered in white thermal protection tiles, was being mated to its cargo module for the very first time. Embossed near the heat shield, its name: tenacity. Dream Chaser at its core is a philosophical rebuke of the capsule. For half a century, the standard way to come home from space has been a blunt cone falling under parachutes and slamming into the ocean. Dramatic, yes, but also messy, hard to recover, and slow to reuse. Dream Chaser asks a simpler question: why not land like an aircraft, launch vertically on top of a rocket, do your work in orbit, then glide home to a commercial runway and do it gently? On re-entry, its crew and cargo experience less than 1.5 times the force of gravity, softer than a sharp turn on a roller coaster. The secret is its shape. Dream Chaser is what engineers call a lifting body, a fuselage that generates lift without traditional wings. That shape lets it bleed off orbital speed gradually, controlling its descent the way a pilot manages an approach instead of falling like a meteorite. The payoff is a reusable vehicle that can turn around fast, land where it's needed, and bring up to 1,750 kilograms of sensitive cargo back to Earth intact. No capsule flying today can match that combination. But none of it works unless the vehicle survives the furnace of re-entry, and that is where Dream Chaser's heat shield stops being a component and starts being the whole story. When a spacecraft tears back into the atmosphere at orbital velocity, roughly Mach 25, about 7.8 kilometers per second, something happens that most people get completely wrong. The vehicle does not heat up because it rubs against the air like sandpaper on wood. That picture is intuitive and it is false. What actually happens is compression. The air in front of the vehicle cannot get out of the way fast enough, so it piles up into a shock wave, a standing wall of violently compressed gas just centimeters ahead of the surface. Inside that wall, motion energy converts almost instantly into heat, creating plasma. Superheated gas, typically around 1,600 degrees Celsius, scraping along the vehicle's leading face. The aluminum frame underneath would begin to melt at around 660 degrees. The margin for error is zero. And there is a second, sneakier problem hiding inside that shock wave. As the plasma cools slightly near the surface, oxygen and nitrogen atoms that had been torn apart recombine back into molecules, and that chemical reaction dumps even more heat directly onto the tiles. How much depends on the tile material itself. A surface that encourages those atoms to recombine becomes, in effect, its own heater. Managing that effect is one of the least talked about but most consequential challenges in heat shield design. Now consider what the space shuttle was working with. Its main tile was made of nearly pure silica fibers, and 94% of its volume was simply air. That near-total emptiness was the trick. Air conducts heat poorly, so a solid that is almost entirely air becomes an extraordinary insulator at almost no weight. These tiles could be heated past 1,200 degrees and plunged straight into cold water without cracking, a level of thermal shock tolerance that is still impressive today. But that same emptiness made them fragile. They had to be shielded from moisture, from aerodynamic loads, from the violent shaking of launch. Each tile needed a glass coating and had to be fitted by hand to one precise spot on the airframe, because the orbiter used roughly 24,300 tiles, every one shaped uniquely for its position. The engineers had a nickname for it: the flying brickyard. The weakness was worst exactly where it mattered most. The nose and the leading edges of the wings, the spots that meet the very tip of the shock wave, were too hot for silica tiles at all. Those areas needed reinforced carbon-carbon panels, an entirely different and more demanding material that had to be inspected and repaired on its own terms. Columbia was lost because a piece of foam struck one of those panels during launch, opening a breach that let plasma pour in during re-entry. One hole about the size of a dinner plate destroyed a vehicle as big as a commercial airliner and killed 7 people. This is the legacy Dream Chaser inherited, and the legacy it was built to dismantle. Tenacity's protection begins with a refined generation of silica tiles, but not the old shuttle recipe. Across the belly and upper surfaces where the heat is intense but not extreme, it uses tiles built largely from microquartz fibers with a small amount of silicon carbide mixed in, and a density low enough to feel almost weightless in the hand. That silicon carbide is not there for strength, it is there for light. It tunes the tile's emissivity, how efficiently it radiates absorbed heat back into the airstream, which is the main way a ceramic tile gets rid of energy during re-entry. The better it radiates, the less heat reaches the structure underneath. Size matters too. Dream Chaser's tiles are larger than the shuttle's standard 6x6-inch tiles, and that has real consequences. Fewer tiles means fewer gaps between them, and those gaps were a constant headache on the shuttle. The flexible filler packed between tiles would sometimes poke up just slightly, tripping the smooth flow of air into turbulence and spiking the local heating. Fewer tiles, fewer gaps, fewer chances for that failure to happen at all. Where the nose and wing edges face the full fury of the shock wave, silica gives way to a tougher material. And here the engineering becomes genuinely elegant. It is a two-piece design. An exposed outer cap made of a high-temperature, low-density carbon-based material mechanically bonded to a base of porous silica insulation. The two pieces are held together with ceramic pins running through the base, a mechanical lock that lets the cap and base expand at different rates under heat without cracking or peeling apart. The advanced version of this material runs about 80 Kelvin cooler than the original under identical conditions. In the world of heat shields, an 80-degree improvement is an enormous safety margin. This material was not invented in a vacuum. It was developed for NASA's X-37 program and then flight-proven on the Air Force's X-37B spaceplane, which has been quietly operating in orbit for years. It has demonstrated reusable performance around 1,600 degrees Celsius and survived single-use exposure to temperatures that would simply destroy conventional silica tiles. And critically, it delivers performance close to carbon-carbon, the most expensive material class in aerospace, at roughly a tenth of the cost and on a far faster schedule. That is the breakthrough that makes a winged commercial vehicle viable. You no longer need the priciest material on Earth just to protect the sharpest edges. And then comes the twist. Even as Tenacity was being finished, its makers were already making it obsolete. Working with Oak Ridge National Laboratory, the team developed a new tile built from a composite of silicon carbide and carbon fibers. The silicon carbide brings stability and resistance to corrosive, oxidizing environments. The carbon fiber brings structural consistency and performance at extreme heat. The new system was validated through more than 100 arc-jet cycles and radiant heat tests at the same NASA facilities used to certify shuttle tiles and Apollo heat shields, including conditions simulating hypersonic re-entry at speeds beyond Mach 17. The data fed directly into the design of the next vehicle, Reverence. The result is a heat shield that does something no shuttle tile ever could. It stays dimensionally stable, chemically inert, and aerodynamically consistent across repeated reentries, without the 4 to 5 months of turnaround maintenance the shuttle demanded between flights. Dream Chaser's ambition is to cut that down to weeks, eventually days. That is not a refinement of how we protect spacecraft from reentry. It is a redefinition of what reentry is allowed to cost. And in the end, that is how the giant fell, not to a louder engine or a bigger budget, but to a quiet company that simply figured out how to come home.